Thank you very much, and many thanks for the invitation to allow me to speak here. It's a great pleasure. And also thanks to Gareth for giving an introduction to ℝexp definable sets, which is what this talk is about. In fact, it's even easier than that. I'm just going to be talking about ℝexp or ℝexp. ℝexp definable is what I mean by ℝexp definable in the title. I'm only going to be talking about unary functions that are ℝexp definable. And it's even easier than that. I'm just going to be talking about the germs at infinity of such functions. So in a sense, there's a singularity there. All these functions tend to have rather bad singularities at infinity. So, so then f equals the, well, I think of them as functions, but really they're the germs at plus infinity of what Gareth called an exp. I think you wrote it like that. Yeah? Definable functions. F just of one real variable. Okay, now I'm going to think of these as functions, but of course, by just considering germs means we identify two functions if they agree eventually. So so two functions are going to be regarded the same if they agree from some point onwards. And what do I mean by definable function? I don't think he ever defined that. So a definable function simply means, i.e., the graph of f considered as a subset of R squared is definable. So is an union exp definable subset of R squared. In other words, when you start with all the restricted analytic functions, just analytic functions defined on an open set restricted to a closed ball within that open set, you make it zero elsewhere, start with those functions and the polynomials and close all your collection of sets under arbitrary, under finite intersections, unions, complements, and projections, and then I just take the sets you get in R squared that way, but of course you might go via sets in R cubed, R to the fourth, and so on, and then project back, but I only take the sets you eventually get in R squared, and for those that happen to be functions, graphs of functions from R to R, that's my collection F, and then, which they needn't even be continuous. Actually, they will always be continuous everywhere apart from a finite set of points. But in any case, they will be eventually continuous, certainly, and that's my set F. Actually, they will be eventually real analytic. So these functions you can consider to be all real analytic functions because they will eventually be real analytic. By the, well, there's an analytic cell decomposition theorem for ℝexp. Now, even if you don't know anything about definability, you'll be able to understand a lot of this talk because there is a characterization of F by Van den Dries, McIntyre, and Marker, which, well, in fact, it's a characterization of all the definable functions, in any number of variables, but it takes a particularly simple form for the unary functions. And let's see, I'm going to bring the top one down because I want to keep that. And I'll have to cover that up for a moment because this one's going back to the top. And I hope we'll stay there. So, okay, so F is, let's see, I think we'll, is the smallest class satisfying the following closure conditions. You will observe that this is a completely logic-free characterization. Okay, one, F is an R algebra, so it's closed under addition, multiplication, subtraction, and scalar multiplication by real numbers. We better say it contains something. Containing the identity function, which I'll just call x. X maps to x. Well, so therefore it contains, of course, the polynomials. Secondly, now there's a little subtlety here. If it's also a field, if f is in F and f does not equal 0, then 1 over f is in F. Now, this needs some explanation. This f not equal 0 means as a germ of a function. In other words, there's some point beyond which it is never 0. So this is, i.e., there exists a y such that for all x greater than y, fx not equal 0. Now, that is, by O-minimality, that's the same as saying it's not the 0 function. Because all functions definable in an O-minimal structure, their 0 set is a finite union of intervals and points. So unless it's eventually 0, it'll be eventually non-zero. So anyway, so that's what I mean there. So, so 1 over f is well defined. Thirdly, we're closed under restricted analytic functions. So if G, so U, an open neighborhood of 0 in R to the n, is real analytic, and I just want to make sure I'm using the same letters. Yeah. And F1 up to Fn are in F, and they converge to 0. If they all converge to 0, as x tends to infinity, incidentally, another property of these functions is if they're bounded, they will tend to a finite limit. Then the composition is in F. Fourthly, if f is in F and f is positive as a germ, in other words, from some point onwards it's positive, which, I mean, this f here, it's a theorem of fact of O-minimality that this is a totally ordered set, so every element is either eventually positive, eventually negative, or eventually 0. Then log f, the function log f of x, is in F. And finally, of course, we have exponentiation. So that was this one. If f is in f, then e to the f is in f. The function x maps to e to the f of x. Okay. And that's all you can do with first-order logic, starting from the restricted analytic functions and the exponential functions. The germs of infinity are characterized by those 5 conditions. They're all got by finitely many applications of 2, 3, 4, and 5, starting, well, and the R algebra operations starting from the polynomials. Okay, that's a complete characterization. I want to add one more condition that's implied by these, but I want to use it later, is a kind of restricted version of this. If f is in f, and for all, and f of x, mod f of x is less than a constant times log x, eventually, so from some point onwards, and remember we have to say that because this is really is a set of germs, then e to the f is in f. Of course, that's implied by 5, obviously, but it's a more restricted version. What it says is that if, when you exponentiate a function, you don't grow faster than the polynomial, then you throw it in. Okay, so the first theorem, as I say, it's the Van den Dries, McIntyre, Marker theorem. I've written their names on. Is that well, I've written it up. F is the smallest class of germs satisfying, of functions at infinity satisfying 1 to 5. Okay. The first theorem I want to present is a classification of the germs of polynomial growth. Now, that won't be a field, first of all. That's the first observation, because, for instance, e to the minus x has polynomial growth, but its inverse doesn't. So it's not a field. But, okay, but nevertheless, they are functions of a certain interest. At least they're kind of a fortiori interest because of what I'm about to say about them. But anyway, so let me give them a name. Let's just call them f poly, yeah. So f poly I define to be the set of functions in f such that there exists an n such that mod fx is less than or equal to x to the n for sufficiently large x, which will depend on n. Okay, now it's fairly clear that f poly is a valuation ring, just meaning a commutative ring with a unique maximal ideal, is a valuation ring. And with unique maximal ideal, well, those functions that go to 0 faster than the inverse of every polynomial. So I'll call it mu, which is the f in f, such that for all n, mod f of x is less than x to the minus n, eventually, depending on n. So for all x greater than some constant depending on n. Sort of Schwartz functions, I suppose. And those are clearly precisely the non-inversible elements in this ring. Okay, so there's the basic Van den Dries-McIntyre-Marker theorem, and okay. Oh, stop. Right. Okay. Right, we'll go on to this one now, I think. Now, so the question I first want to answer is, so we have a evaluation ring F poly, we have its maximal ideal, so F poly modulo mu is a field. It's a set of, well, it's not a set of functions in any sense, but it's a set of functions modulo an ideal. And the first theorem I want to present is a characterization of that field, or rather a kind of canonical set of representatives for that field. So the first theorem is, and this is why I wrote the phi prime, let F res stands for residue, as in residue field in the theory of valuation rings, denote the smallest subclass of F satisfying closure conditions that's a long way up. 1 to 4 and 5 prime. Okay. So we don't close under full exponentiation, we only close under exponentiation providing it results in something of polynomial growth. Well, then the theorem is that F res is well, it's certainly a subfield of F because we have inverse there. We have closure under 2, but it turns out to be a subset of F poly. Now, that is not quite obvious. You might look at all those conditions and say, well, obviously, the polynomials have polynomial growth, and polynomial growth is preserved by the R algebra operations. It's certainly preserved by 3. In fact, you only get bounded functions from 3. Obviously, if f has polynomial growth, so does log f. And we only exponentiate if we get polynomial growth. But the problem is number 2. You see, you might get something in mu by, well, you might be able to combine. You might get 2 functions that end up being very close together, and when you subtract them, you get something in mu, and then you invert them, and you get something that's of greater than polynomial growth. Now, it turns out that that can't happen, and so F res is indeed a subset of F poly. Now, I don't know of any real proof, any direct inductive proof of that fact. I'm going to have to use some complex analysis, which I'm going to explain in a minute, to actually even prove this. But more interesting, well, further, in fact, F res consists, well, let me put it like this. F res is isomorphic to F poly modulo mu. So in other words, F res contains exactly one element from each equivalence class. So it's a representative of this residue field. So F res contains exactly one element from each class F mod mu for F and F poly. So it kind of gives us a canonical representative of each function of polynomial growth modulo mu. So, of course, if we take the functions in mu themselves, then that's 0. That's the 0 function, is picked out, nothing else. And, well, so it's perhaps slightly surprising that all we have to do is restrict the exponentiation, and we get full representatives of the valuation ring. Okay, so that's the first theorem. Now, this requires some model theory. I'm not going to go into the proof of that. It works best if you work in a non-standard model. Incidentally, for those that know, F is itself a non-standard model of the theory of the reals with restricted analytic functions and exponentiation. And that's the best way to view it when proving this. But that's quite heavy model theory, and I won't go into that here. Now, perhaps the surprising thing, so that's the first theorem. The second theorem is, okay, so that's theorem 1, and I won't say much more about it. Theorem 2 is the following. Every F in F res has a complex analytic continuation. Well, they're only germs of functions, so of course here I'm taking a sufficiently large real number A and regarding this as a function from A infinity to R, has a complex analytic continuation to some half plane, to some right half plane. And I'll call the analytic continuation F hat, so it's from the set of Z in C, such that the real part of Z is greater than A for some A to C. Perhaps that's not so surprising, because all the functions that go into making up the functions in F, or not just F res, but F, have analytic continuations, but of the same growth, so such that F hat Z, mod of F hat Z is O of F of mod Z. Okay, so it grows roughly the same as F does, as uniformly as mod Z tends to infinity. So it has a complex analytic continuation of roughly the same growth. Of course, other functions in F do as well. I mean, e to the z, e to the x, you can extend to e to the z, and even this is true. But something more happens to be true here. Now I'm on the middle one, I think. Yeah, right. Further, F hat considered as a function from, considered as a function from a subset of r squared to r squared via its real and imaginary parts, is ℝexp definable. So the subset, I mean this plane, this half plane considered as a subset of r squared. So this set considered, the graph of this function considered as a subset of r to the fourth is in fact an Rnx definable set. And that is not true for any other functions. Further, also, the f in f-res are the only f in f with this property. So this completely is another characterization of f-res.
X to the pi is from here.
Sorry?
X to the pi is there.
X to the pi, yeah? X to any real number is here, and that extends to z to the real number, which can be extended to a half plane, and it doesn't grow any faster than it does on the real axis, yeah. Right? This is not the real part of z here. That would obviously be false. It's mod z. I mean, you just have to consider the identity function, and that sort of grows on the imaginary axis the same as it. So you have to go around the circle. This includes, that's a good point, actually. This includes all real powers of x, which extend to the corresponding real power of z. But those are perfectly innocent complex analytic functions on a right half plane. No, you can't go round. Yeah, no, you can't go round, though. We're only on a right half plane. So, okay. Well, perhaps actually, what time do I finish? Is it 10 past? 10 past. Okay. So I was hardly going to say anything about the proof of this, but since you've raised that, that's a nice point. So the crucial point is this. If, let's say, f from the real part of z greater than a to c is analytic, complex analytic, and definable, and an union exp definable, or actually definable in any minimal structure. Actually, only continuity is needed for this, not even analytic. Then, writing fz equal r of z e to the ei theta z in the usual way, it's definable and non-zero, sorry. Then that means you can find continuous functions, real-valued functions r and theta, so r theta continuous. We have, well, of course, we have mod f is definable. That's easy. So if you have a definition of the real and imaginary parts of this, this becomes definable. And so therefore, e to the I, the function z maps to e to the I theta z is definable. But the crucial point is to show theta is definable. Now, well, this is definable. This means i.e. cos theta and sine theta are both definable. Now, in general, if the cosine of a function is definable, why is the function itself definable? You wouldn't take cos to the minus 1, but of course that has ambiguities. Well, the point is that because this is definable, you can look at the points z such that this takes the value 1. Okay? Now, that has to be a finite union. That can only have finitely many connected components. That's a property of O-minimal theories. And that clearly implies theta has to be bounded. So cos theta is definable, and therefore theta is bounded. Because if it weren't, the points z at which this equaled 1 would have infinitely many connected components. And that can't happen in any O-minimal theory, in particular ℝexp. And so theta is bounded, and, well, we know that the inverse cosine on a, if you take the inverse cosine on a bounded set, there's a way of doing that. You only have finitely many ambiguities, and that can be dealt with. So that says, therefore, theta is definable. So the one crucial step in the proof of this is to prove that if you have any definable function from a half plane, then its argument is bounded. And the argument is definable here. So that means you can take its log. That's crucial in step, which is it, 4. Mod f is definable, so log r is definable, but you need I theta, or you need theta to be definable to be able to take the full complex log. And because theta is bounded, you can take log theta will be definable. So that's a crucial step here. Once you've done that, it's not so hard to show that if a complex function is bounded by the logarithm of z, the mod log z, then it has the property that its imaginary part is bounded. That's a modification of this argument. So therefore, you can take its exponential definably. You see, e to the z itself is not definable for a similar reason. If you look at the points at which it takes the value 1, that does not have finitely many connected components. However, you can always take the exponential of a function whose imaginary part is bounded, because you're allowed cosine and sine on bounded intervals. So anyway, so the O-minimality is used very crucially in getting this complex extension. Okay, so those are the main theorems about ℝexp definability that I wanted to say. Now let me just give this a very quick sketch of how you get Diophantine information from these complex extensions. So this is the middle one. Yes, I think we'll have this one. Yeah, I can come there. Yeah, that'll do, right. Right. Okay, so an application of this is a theorem. Now, as you've heard from Gareth Jones's talk, we're very interested these days in Diophantine properties of sets definable in O-minimal structures. So here's a theorem that goes way beyond, well, it's only about unary functions, but apart from that, it goes beyond the Peeler-Wilkie theorem. Unfortunately, it only deals with integer points rather than rational points. But, okay, so the theorem is if f from R to R is an union exp definable and has growth less than or equal to some power of x times 2 to the x. 2 to the x, very important. You can't, unfortunately, increase the number 2 here. Eventually. And if it happens to take integer values at natural number points, then it can only be the obvious example of such a function. It can only be of the form p of x times 2 to the x plus q of x, where p of x and q of x are polynomials. Well, you can't say with integer coefficients, because obviously this could have a half in there. But with rational coefficients. Right, now this goes way beyond the Peeler-Wilkie theorem because, well, but it's got limitations. So the Peeler-Wilkie theorem is about arbitrary sets in R to the n. But you see, if you look at the graph of f and you look at an h, the number of this assertion just says there's roughly log h integer points of height h, right? Because of the exponential growth here. That's nowhere near h the epsilon, so we can't apply that theorem. But on the other hand, we're only looking at integer points, so we might look at, you might expect something better. Now, perhaps if I could, you're probably more interested in the general method, which is due to Polya, it's about 90 years old, than my modification. So let me just tell you about that. So Polya, in 1921, proved the same result for entire functions. And then, well, in no sense can we assume f is entire, but with a bit of luck by this theorem, we can at least suppose maybe it's analytic on a half plane, well, except that this theorem only applies to functions in f-res, and they have polynomial growth, and this doesn't. So I'll just say something about that in a minute, if I can. But anyway, the important thing about applying complex methods is that it wasn't actually until 2007 proved the same result for functions analytic in a right half plane. Okay. So that immediately implies the result via this, that, well, for functions in f-res, it proves they must be polynomials if they take integer values for natural number arguments. But we've known that for arbitrary O-minimal theories for a long time anyway. But okay, so it's really this method that I generalize, or I'll try and make plausible. But let me give you, because it's so nice, Polya's method. So he takes, so you take any function f from n to the complex numbers, and you want to somehow reduce its growth until it gets down to tending to 0, and then, of course, if you happen to know it takes integer values, it must be 0. Now, the usual way in these arguments of reducing the growth of a function is to differentiate. And certainly, if you're a function that's significantly below e to the x, then differentiating will reduce its growth. However, differentiation doesn't preserve this property. Right, a derivative of a function with this property by no means has to have that property. However, Polya's method is to look at the difference operator, which does preserve that property. So we define a function delta f. This is just defined to be delta f of x plus 1 minus f of x. And of course, that operator does preserve this property. And it behaves a little bit like differentiation, and it will slightly reduce the growth of your function. But it's even better if you keep doing it, so one iterates this. So this is just... So clearly, if f of n is contained in Z, then delta n of f of n is contained in Z for all n, right? So it preserves taking integer values for natural number arguments. Now, I assume this is Polya's theorem, but I don't know. It might be a lot earlier. The theorem is that if delta nf of x, n, k, 0, is identically 0, well, it is 0, for sufficiently large n, that can only happen if f is a polynomial. Obviously, it happens for polynomials. Because you reduce the degree every time you take the difference operator, so you eventually get down to the 0 function. But if just applied to 0, this is not quite so obvious the other way round. So if delta nf is 0 for sufficiently large n, then f has to be a polynomial. Right, I'm now... so Polya's method so Polya shows that if f from C to C is entire, and f of z, okay, I'm now going to prove a special case of my theorem when the n is -1 in the theorem. So I'm going to just look at functions which are little o of 2 to the mod z and prove they're polynomials. That when you multiply it by a power of z, that adds a slight extra technicality, but it's not so difficult. Then, for any entire function, he shows that actually delta nf of 0 converges to 0 as n tends to infinity. So therefore, if f of n is contained in z, so therefore for all n, delta nf of n is contained in z. So if it converges to 0, it has to be 0. So we have delta nf 0 equals 0 for all sufficiently large n. So therefore, from this theorem, f is a polynomial. Now that basic method still appears in Langley. Well, let me just give you the complex analysis that does this. So I'm sure you will have all now worked out the formula for delta nf of f. So the sort of proof is we have delta nf of 0 is sigma, as I say, as you all will have calculated by now, n factorial over k factorial n minus k factorial f of k. Okay, just you can see the binomial coefficients coming in when you iterate this. So that's the formula for any function defined on the natural numbers. But what extra information can we get from the fact that f is entire? Well, if f is entire, there's a very clever way of writing this. So this is Polier's idea. You simply write that as 1 over 2 pi I round the circle mod z equals 2n. N factorial fz dz over z minus 1 up to z minus n. Okay, now can you see why that's true? Because if you look at the residues here, this is just the sum of the residues of this function, because, for instance, if we take z equals 0, we get a -1 to the n times n factorial on the bottom, and that's precisely what we get here for the k equals 0 term. We get -1 to the n. And of course, if you use the deletion rule when you take out the z minus k, the kth term here is precisely the residue at z equals k of this function. So you've got the fk here. So that's the clever idea. Now you just use the bound. This is less than. Well, the size of this circle is 4 pi n, and you've got 2 pi there, so you get a 2n times, well, on this circle, this is bounded by n factorial over 2n minus 1 down to n, times the bound of this function, which is little o of 2 to the 2n, right, on this circle. Now, this is just the, oh, have I missed out? I missed out an over 2n somewhere. Oh yeah, I've got, I want to, yeah, let's suppose this is little o of just a, yeah, you have to be a bit more careful with Stirling's formula, but let me just suppose that's over mod z there. So that will give me an over n here, so I can cancel it with that. And And this thing here is just 1 over the binomial coefficient 2nn. Now, the binomial coefficient 2nn is roughly 4 to the n, because if you think of the expansion of 1 plus 1 to the 2n, it's one of the terms. So that's approximately 1 over 4 to the n, which then cancels with that 2 to the 2n, so that tends to 0 as n tends to infinity. So we've done that very quickly, but that's where the complex analysis comes in. It was important here you had a circle. If you've only got a half circle, which you would have in Langley's method, where it's only analytic on the right half plane, is that you have to be a bit more careful on the vertical line to estimate this, but that's just an analytic technicality. Okay, that's what you do if the function is entire, or if it's analytic on the right half plane. Of course, we don't quite have that. So, oh, sorry, can I just make the point that if f is in F and mod fx is, say, little o of 2 to the x over x, then what we do is we look at f of log x, and that is in F poly, and therefore very close to a function in F res, which has the required analytic continuation. And you have to work throughout with f of log, so you have to put log z here and calculate the residue and use a big circle of radius 2 to the e to the n. But that's just analysis. The crucial point is that by substituting a log here, you can get a function now in F poly, and you approximate it very well by a function that has the analytic continuation. And it's so well approximated that you can go back to the integer valued function, and tending to 0 here is still sufficient to deduce that when you go back to the approximated function, it must be 0. So, sorry, that was a bit rushed at the end, but thanks very much.
Blaise? Yeah. You have to take the microphone.
Or I can repeat the question.
Yeah, coming back to theorem 1 and theorem 2,
yeah.
If you have some non-polynomially bounded or minimal structure,
yeah.
which is not this one,
yeah.
How
no,
this theorem
may well not be true. The one consequence, a real consequence of this fact, is that okay, it's true in any O-minimal structure that if a function is bounded by a polynomial, say x to the k, then its derivative is eventually bounded by x to the k minus 1. Okay, that's true in any O-minimal structure. But as far as I know, and you can keep doing that even if k is not an integer, and you can go below 0, the point at which that inequality holds depends on k. So when you differentiate, so if you want to get down to x to the k minus r for the rth derivative, the constant beyond which that tends to hold will depend on r. But one consequence of this is that it doesn't. For r and exp, you can get a fixed c such that any function of polynomial growth is bounded by the function divided by x to the r, the rth derivative bounded by x to the r, from the fixed point onwards that doesn't depend on r. That's just a consequence of the residue formula for the derivatives. And that doesn't hold in an arbitrary O-minimal structure, as far as I know.
So
so this definitely, I definitely use the construction of the functions f used by from the closure conditions 1 to 5 to prove this. And there's no such theorem of this for any other O-minimal structure.
Right.
No such characterization.
So that you can have examples, let's say, of O-minimal structures where this holds and where this doesn't hold.
Now, do I have an explicit example?
In this one.
I'm not sure I've actually constructed an explicit example where this doesn't hold. My guess is that something involving the gamma function, which is still O-minimal, or log of the gamma function, something like that, it wouldn't hold. Yeah, well, you'd have to work out what the closure conditions are. I suppose you just put in gamma of f, it's in it, if f is. You see, this all relies on a very nice quantifier elimination for R and X, and the universal axiomatization. And that we don't usually have in arbitrary O-minimal structures. So this relies not just on the O-minimality, it relies on the logic.
Yes, this is clear, yeah. I wanted to see
That's right.
Up to what extent it's applicable.
Yeah, I think probably, I don't know any other structure to which it's applicable. But nevertheless, I made the effort to prove these because R and X does have wide applications, just that structure.
So that you can probably just have a sort of function of polynomial growth whose extension, who doesn't admit any extension,
my guess
who
is,
has no essential singularity, something like this, right?
Yeah, that's right. It will have, right.
If you find a function like
poles,
this.
Actually, yeah, my guess is that you can have that. But I don't know an explicit example.
Yeah. So if I understand well, theorem 2, in your application, you use theorem 2 to approximate the function with a function in f residue.
Which
and you apply
S.
the Poyer method. Yeah. But how you guarantee the condition that f of n is contained in Z?
You don't. You just apply the method to the approximating function, and that you still get that the approximating function converges to 0 at a rate you can estimate, and then you now okay, so the approximation of f is so good that all the differences approximate it as well, because when you put an exponential in, the approximation is better, much better than the inverse of all the binomial coefficients that occur here. So it approximates the delta function applied to the function as well as the function itself. So you prove that the approximating function tends to 0 as well. But that function is integer valued, so that one is 0. No, you can't use anything about the approximating function, but you end up